Okay, so last time we talked about, towards the end, we talked about sequences. And so in particular, we talked about square root of 2. Right? So square root of 2, we could think about this, if we wanted to think about square root of 2 on the real line, then we have here 1 and we have 2. And we could define a sequence of numbers where the first one is 1, the second one is 1.4, the third is 1.4.1, and the next one is then the next digit in square root of 2, so 1.4.1.4, etc. And so, so this is like a sequence of numbers that are increasing, and it is square root of 2 where you're taking more and more digits, right? So square root of 2 is in some sense the limit of this sequence. And so precisely a sequence is, so we talked about that last time, but let me just remind you what that is. So a sequence is a function from the natural numbers. So f goes from the natural numbers into the real. And the value at some natural number n, the value of this function at a natural number n, this we denote. Usually it's a standard notation that one denote it like this, where the n is a subscript. Okay. And so let's take a look at a couple of different sequences. So we talked that. So this here really is a sequence. Another example is where you have an equal to -1 to the power n. So, so n again is this natural number. So this means that the sequence a1 is equal to -1. A2 is equal to -1 times -1, so that's 1. A3 is -1 times -1 times -1, so this is -1, and A4 is -1 multiplied itself 4 times, so that's 1. Right, so this sequence here is, it's alternating between the values -1 and 1. So it's starting off at -1, and then it goes to 1, then it goes to -1, 1, -1, etc. Okay? And so this sequence here, right, it doesn't really, right, it's not, you know, it doesn't really converge. It doesn't really have a limit, right? So this here, we'll make this precise in just a minute. So this sequence does not have a limit. An example of a sequence is a decaying sequence like this. So an is equal to 1 over n. Right, so a1 is equal to 1, a2 is equal to a half, a3 is equal to a third, and then a4 is equal to 1/4, right? So these numbers here are all positive, right? The values of a is all of them are all positive, and they become smaller and smaller, right? So you could write that sort of suggestively, this here is going down like that. And so, right, so it seems sort of obvious that this limit here, that this sequence has a limit, this here has a limit. and the limit is 0. Okay, so now let me make the formal definition. So what does it mean that a sequence is convergent? So a sequence, AN is convergent to A. So A is another real number. Is a sequence AN is convergent to A if the following is the case. If the following holds. For all epsilon greater than 0, there exists an natural number such that if little n is bigger than this natural number, then the difference between AN and this supposed limit is bounded by epsilon. Okay, so if you think about it, on the, here you have on the real line, here you have A. And so if you give me an epsilon, so then I'm looking at A here, I'm looking at an interval around A. So this is an interval here from A minus epsilon to A plus epsilon. And the claim is that the sequence AN is converging to A if there exists some n, so that if little n is larger than this capital N, then all of these AN land somewhere here, right? All of them AN is in this little interval for n, little n bigger than this capital N, right? That's what it means to be convergent, right? But it's like for all epsilon, so you are allowed to, someone else is allowed to pick the epsilon, and then you have to prove that there exists a capital N, so that from there on and out, all of the AN lie in this little interval. Okay. So this is what it means for a sequence to be convergent. So we say that AN is convergent to A if this here is the case. And in that case, one also writes that the limit as n goes to infinity of AN is equal to A. A sequence, so if you have a sequence that is not convergent, is said to be divergent. Okay? And so now let me look at an example. So suppose you're looking at the number 0.99999, etc. Right? This number here, this number here, we really think about this number here as 1. This is indistinguishable from 1. Right? And in fact, what you really think about is that you think about that you have a sequence A where A1 is 0.9, A2 is 0.99, A3 is 0.999, A4 is equal to 0.9999, etc. Right? So AN is where you have 0. And then 9 n times. Right? If you're looking at that sequence here, right, then you have that this sequence AN is convergent to 1. So AN, this one also write that is convergent to 1 like this. So AN is convergent to 1, right? So there's various ways of writing that is convergent. You can write it like this. This means that it's convergent and the limit is A. You can write it like this. This means that the sequence is convergent and the limit is 1. Right? Or you can write it out in words. Okay. So this sequence, I claim that this sequence here, defined like this, and this is really how you think about this, right? When you think about this number, you sort of think about it that, this is, 0, 9, 9 with more and more numbers, 9s added, and the limit, which is really what this number here in itself is 1. Okay, now let me explain why the sequence defined this way, why this is convergent as a limit 1, okay? And so now, of course, now you give me an epsilon. So given epsilon greater than 0, then I need to find a capital N so that from there on and out, the AN is within epsilon. So we need to find, for this epsilon, we need to find capital N so that if little n is bigger than this capital N, then AN minus 1 is less than epsilon. Right? That's what we need to do. Right? But for your epsilon, so to do that, we need to choose this capital N. So I'm just choosing, I just choose capital N. So to do that, choose capital N such that that 1 over n is less than epsilon, right? We can do this by the Archimedean property, right? So this is, so we can find n by the, such an n, and capital N by the Archimedean property that we discussed last time. Okay. But now you see, if you're looking at, if you now look at little n that is bigger than capital N, then you have that 1 minus an. Well, 1 minus an, actually, for all n, this here is less than 1 over 10 to the power n, right? Because like if n is equal to 1, this is within 1/10 of 1, and likewise this here is in 100 of 1, etc. Right? So we have this inequality. It's actually equality in this case. This here is an equality. Right? Okay, but now you see that this thing here, this is obviously 1 over 10 to the power n is less or equal to, it's less than n, 1 over n. And so if little n is bigger than capital N, this is therefore less than 1 over capital N, but this here was less than epsilon. And that's what we needed to prove. Right? So for your given epsilon, I specify a capital N, and then we need to prove that if little n is bigger than that capital N, then we come within epsilon of the limit. Okay. Okay, now let me prove a little theorem about convergent sequences. And this is like, if you will, this little lemma is like the first test for whether a sequence is convergent. So theorem. If an is a convergent sequence, then an is bounded. Sorry, let me explain what I mean by that. I mean that then the set of an, so just explain that. So then the set A1, A2, A3, etc. This set here is bounded. Okay. It's not enough to be bounded, that to be convergent, but it is a necessary criterion. Right? Let me just, as a side remark, say that if you're looking at the sequence an that we looked at just a minute ago, this here that is alternating between -1 and 1, right? This is a bounded sequence because there's only 2 values, so it's obviously bounded, but it's not convergent. Right? So, but it is a necessary for a sequence to be convergent. It's necessary that the sequence of numbers here is bounded. Okay, so now let's try to prove that. So we have, so since an is convergent, then there is some a so that an converges to this a, right? And so now I can just focus on one single epsilon. So in particular, if we choose epsilon to be equal to 1, then there exists capital N, so that if little n is bigger than this capital N, then a little n minus a is less than 1, right? This is convergence just applied to this single epsilon, right? Okay, and so now, so this is the first observation. The second observation is that if we now look at all the an that are not considered here, so if you're looking at the set, this is the first capital N minus 1, an, right? Those are the ones that doesn't fall in under that this little n is bigger than the capital N. So this set here is finite. So obviously, so for any finite set, you have that, so there exists C, a real number, such that an is less or equal to C for any of these guys, right? For any A in this, any an in this finite set. Right. So this means, in other words, this means that an is less or equal to C if n here is between 1 and n minus 1. Right. So now I look at, now I want to look at the numbers an and this number here, right? And I want to look at, so I'm thinking about the set an absolute value, and where n here is 1 up to 1, 2, etc., right? Well, I claim that this thing here, I can now prove that this set here is bounded. And this is just because that the first n minus 1, those are bounded by C. So I claim that this set here, so claim is that the sup of this set, where n from 1 right over all n's, the sup of this set is less or equal to the max of C and A plus normal absolute value of A plus 1. So I claim that. Right. Now this is clearly, if you're taking the first n minus 1, then we already know that they are bounded by C, right? So you just need to worry about the one starting at capital N, right? So we only need to worry about when, so this is obviously the case for the first capital N minus 1. So we only need to worry about, to show this for little n larger than capital N, larger or equal. Yeah?
Are you able to explain using the max over there why there's the absolute value of A plus 1, like the plus 1?
Yeah, I will explain this, and I'll get to this. And this is part of the proof. Yeah. So it hopefully will be clear in a minute. If it's not, you should complain. Okay, so I only need to prove that when I'm just looking at the set here and I'm starting at capital N, then the sup is bounded like that. Right? And so then I'm looking at an, but an I can write as an, I can write sort of in a stupid way. I can write an as an minus A plus A, right? So I can write it like that, right? And then I can just write, so I have the sum of two things. The absolute value is less than the absolute value, the sum of the absolute values. So I have this, right? But now you see that since little n is bigger than this capital N was chosen so that this here was bounded by 1, right? So this thing here is less than 1, and this here is less than the absolute value of A, right? And so we have, for the whole tail, starting at capital N, we have that this thing here is bounded by 1 plus the absolute value of A. And for the remaining capital N minus 1, those are bounded by C, right? And so together, all of this is bounded by the maximum of these two things. Okay. Now the next thing I want to talk about is that there's some sort of algebraic property of limits. That is often very useful. And I will prove there's 4 of these. And I will prove 2 of them. And the other one I will outline the proof of. Yeah.
So in that, the claim was that the soup is, the soup is less than. So we don't need to find.
Yeah, no, you don't need to actually find the soup. Fine. Yeah. And the reason I want to write soup and not maximum is that, of course, if it's infinite numbers, it's not clear there is a maximum, right? So we need to use the terminology soup.
So that max of C and abs A plus 1 is not the soup?
No, that's right. It's a bound for the soup, but the soup presumably is less.
And 1 there really is just epsilon, right?
And the 1 really, to some extent, could be almost anything. Yeah, it came from the epsilon, right? But you see, if you made that epsilon smaller, then probably the C would jump up, right? Because that is, right? Because the C was the maximum of the first n minus 1. So if you're further out, then there are more numbers that you're taking the maximum over. So anyway, yeah. Okay, so we want to prove some algebraic properties of limits. Okay. So the idea is that we take, so we have 4 of these. And the first one is that you take a sequence. So maybe I'll just say throughout, AN and BN are sequences. And AN is convergent to A, and Bn is convergent to B. Okay. The first property is that if you take a real number, C here is a real number, and you form a new sequence where Cn is just this real number times An, right? So each Cn is somehow almost like An, except that they're multiplied by this fixed constant C. So this here, so the first one is that Cn is also convergent, and the limit is just C times A. Okay. The second one is that that if you take that A, if you define a sequence, so this is a different sequence than this one, but if you define a sequence Cn by its An, the nth element is An plus Bn, then this sequence is also convergent. Cn is convergent, and the limit is A plus B. So that was the second property. The third property, is right. The third property is that if you take a product. Sorry. So if you take An, if you define Cn as An times Bn, right? So this is a new sequence. Then Cn is convergent, and the limit is A times B. And the last property is that if the An are all of these are different from 0. So this here is for all n. And also you have that the limit here is not equal to 0, then if you define a sequence to be 1 over an, then Cn here converge, and the limit is 1 over a. Okay. And so I will prove sort of rigorously the first two, and I will basically tell you how to prove the other two. But the first two I will kind of write out formally as as we talked about last time, how you write formally a proof. Whereas what I'm going to discuss for 3 and 4 is very, very close to a formal proof, but it's more like what you would have on a piece of scrap paper. Okay, so now let's prove the first one. So proof of 1. So given epsilon greater than 0, So first of all, of course, if this capital C is 0, then everything is 0. So it's like trivially the case. So we may as well assume. That's capital C. That capital C is not 0. So now, given epsilon greater than 0, since this sequence an is converging to A, this means that there exist n such that, and now I'm not going to use that epsilon. You gave me that epsilon. I'm not going to use that epsilon in the definition that an is converging to A. I'm not going to use that one, but I'm going to use one that is closely related. I'm going to use epsilon divided by the norm of C, right? Because that's another positive, right? So you gave me an epsilon. I'm going to look at this number here. That's a positive number. And I can use that in the definition that an converts to A. So I'm going to say that because an converts to A, there exists a capital N such that if little n is bigger than this capital N, then an minus A is less than epsilon over capital S. Capital C, a norm of capital C. Right? But now I just multiply on both sides, so multiply by the absolute value of capital C on both sides. And so if we do that, then this here pops in, right? It actually go in as C times an minus C times A is less than epsilon. And this is as long as this n, little n is bigger than that capital N. This is exactly what we wanted to prove. Right? Okay, now the second one is right, so the reason why I'm doing the first two, you see that those are pretty straightforward. I mean, it's not like that. It's not like any of these is complicated to prove. The next two is a little bit more. I mean, I wouldn't say complicated, but a little bit more involved. These two, but I want to give you the idea because it's a kind of a very simple but useful idea in these two. So I don't want to skip the proof. Okay, so now we want to prove of the second property. Okay, so we have that AN is converging to A, and BN is converging to B. And so again, you give me an epsilon that I have to work with. So given epsilon greater than 0, then I'm going to not again use this epsilon in the definition that AN converts to A, and I'm not going to use it in the definition that BN is converting to B, but I'm going to use epsilon over 2 in each of them. So since AN converts to A, there exists a capital N, and let me call it capital N subscript A, such that if little n is bigger than this capital N subscript A, then AN minus A is less than epsilon over 2, right? And likewise, since Bn converts to B, then there exists a capital N, but and I noted by this may be different than the one coming from A, the sequence AN, such that if little n is bigger than this capital N subscript B, then Bn minus B is smaller than epsilon over 2, okay? And so now I have to choose, right, so you gave me the epsilon and I have to choose a capital N. I haven't chosen that yet, but I will do that now. So we're set capital N equal to the maximum of these two n's. So you're setting it equal to the maximum of these two. Now if little n, so then for little n bigger than this capital N, if you're looking at A, so now we want to look at, so our sequence Cn was the sum of these two, right? So this here was Cn. So we want to prove that, so we want to look at Cn minus A times B. And we want to prove that if little n is bigger than this, then this here is strictly less than epsilon, right? But this thing here is Cn was by definition An plus Bn. Sorry, and this was not the product, it was a sum. Minus A plus B. So, but this thing here you can write as An minus A plus Bn minus B. And now you can just take the absolute value of this. It's bounded by the absolute value of the first. So plus the absolute value of the second. Right? And now you see that if little a, let me keep, so if little n, since little n is bigger than capital N, which is bigger than capital N of A in particular, then this thing here is less than epsilon over 2, right? So you have that Cn minus A plus B is less than epsilon over 2. That comes from this. But you also have that capital N is bigger or equal to N sub B. So you also have that this thing here is less than epsilon over 2, right? So you have that this thing here, when little a is N is bigger than this capital N, this thing here, this difference is strictly less than epsilon. That's what we needed to prove in order to prove that this sequence, that was the sum of the two sequences converging to the sum of the limits. Yeah?
When we initially defined like N minus B or N minus A be less than epsilon over 2, what was again the justification for why we could say if we know that N converge to be within like...
Right, so that's right. So because AN or BN, because they converge, so like say AN converges to A, right? Then for all epsilon, you gave me the epsilon, and I'm using that it's converging not just for that choice of epsilon, but also even for epsilon over 2, right? That epsilon, so you gave me the epsilon, then I'm using that it's converging, so I will have to choose probably an N that is much larger if I'm using epsilon over 2 than if I use directly the epsilon.
Right. So that assumes that as N increases, like epsilon gets smaller.
As epsilon gets smaller, presumably you need to choose capital N larger.
Okay, so you couldn't run into a case where we're assuming like the convergence is like smooth as opposed to like oscillating about it.
Right, that's right. I mean, right, I'm using that I'm basically using that for all epsilon, that it wasn't just for a fixed epsilon, right? And so that's why when you came with this epsilon, then I'm actually used it for epsilon over 2, yeah. Okay, so that was the first two properties. Those were it's not like the other one is super difficult, but those two are the most straightforward. Let's look at the other two. And so, right, in particular, because it's like for the next one, there's a little trick that is useful in various different settings. And so prove, but the next two I will just outline, okay? So proof of 3. So outline. So we need to look at AN times BN, right? So CN is AN times BN, and we want to compare CN with A times B. Right? We want to show that this thing here, if little n is sufficiently large, so given epsilon, if little n is sufficiently large, then this difference is bounded by epsilon. But this thing here is AN BN minus AB. Okay? And so the little trick is now that in itself, it's kind of difficult to compare these two things. But the little trick is that if you're looking at AN, BN, if you sort of, instead of comparing them directly, then comparing this with something that is halfway between this and that, then it gets a lot easier. So what you do is you're looking at AN, BN, and you subtract AN, B, and then you add it immediately again. So this is certainly the same, right? And now I can write this thing here as AN. I can just concentrate on these two first, and there I can factor out an AN. So I can write that as this. And this thing here, I can factor out a b. Right? So I can write it like that. And now, now you see this is like, it looks much more promising. This one looked like the problematic one. This one looks like no problem at all, because this is just some fixed constant times this difference here. This one looks a little bit more problematic because it's not a fixed constant, right? But we'll deal with this in just a second. But the first thing I can do is I just take the absolute value of this, plus the absolute value of that. And now I just take, so then this here is actually the same for a product. You can just take the product of the absolute value. It's the same. Okay. Now, the next thing is that we're going to use the theorem that we proved earlier. That since this sequence here, since these numbers here, all of these numbers for all, when you take, right, when you take the set, when you're looking at this set here, since this set here is bounded, and it's bounded because the sequence was convergent, right? And so we already proved that then the values, the set of values is a bounded set, right? So it's bounded. And so we can assume, so there exists C, so that AN is, the absolute value is bounded by the C, right? And so now, I have, okay. And so now I have that Cn minus A times B. This is what I had up there. And I'm just using that this is now bounded by, just because these things here are bounded by C, I get C, B n minus B plus B over AN minus A. Right? And now you see, now it's going to follow like, so this here was just some observations, right? And now when you come to the proof, so to prove 3, then given epsilon greater than 0, now we want to make sure that this thing here is less than epsilon over 2, and that this thing here is less than epsilon over 2. And so I don't want to get in trouble if this here was 0, or if this here was 0. So I'm just, so given epsilon, since AN converts to A, then I can find, now I'm basically writing out the whole proof, but AN, I can find capital capital NA, so that if little n is bigger than capital NA, then you have that AN minus A is less than, I don't quite use that epsilon, and I don't quite use epsilon over 2, but I take absolute value and multiply it like this. Okay, because I don't want to have something where if B was 0, then it really didn't make any sense what I wrote. So now there's no problem. It definitely makes sense, even if B is 0. And likewise, since so likewise, likewise, sorry, since Bn converges to B, then there exists, so again, you gave me a epsilon, so there exists a NB such that if little n is bigger than NB, then actually you have that Bn minus B is less than epsilon, again, over 2, and this is not quite what I use, because I don't want to be in trouble that C is already non-negative, because it's bigger than these absolute value. So, but I'm just adding 1 for the same reason. And so now you see that if little n, so therefore, if little n is bigger than the maximum of these two, then both of these inequalities hold. Right? Both of them hold. And so this means that you now have that Cn minus A times B. This thing here, so we had it here, this is less than C, and then this difference here was now assumed to be epsilon over 2, 1 plus C, and likewise, this thing here is bounded by this number here times, and then this thing here. So epsilon over 2 absolute value of B plus 1. Okay. But now you see that this thing here, that C divided by 1 plus C, that's bounded by 1, right? So this thing here is bounded by epsilon over 2. And this thing here, same reason, is that this thing here is bounded by epsilon over 2. And so the whole thing was bounded by epsilon when little n was bigger than the maximum of these two. So this, in the end, I wrote out the whole proof. Right? I already posted the lecture notes. In the lecture notes, I didn't write out the whole proof, but I gave the idea. So I sort of stopped once we were here and somewhere here after this one. Somewhere, anyway, well, you see. Okay, so the next thing I want to talk about is that if you, I still need property 4, and that's also useful. Sorry, so let's go through that, and then we'll come to subsequences. So I want to prove that if you take a sequence of real numbers, none of them is 0, they converge, and the limit is not 0, then 1 over the sequence is another convergence sequence. Okay? But again, just the main takeaway, I think, from property, this third property was that this little idea about inserting something that was halfway between the two things you were comparing, because they weren't very easy to compare directly. And that's like a little trick that is useful in various places. It comes up almost the same thing. One place it comes up is what's called Leibniz rule, that if you take two functions and you take the product of these two functions and you try to prove that what is the derivative of the product, it's exactly the same trick. And it comes up various other, more fancy ways. Okay, so now let's prove property 4. So property 4, proof of property 4. So we have this, so Cn is 1 over An. And we know that An are not equal to 0, and we know that A is not equal to 0. This here makes sense, and also 1 over A makes sense. So we want to compare this here with 1 over A. And so this thing here is 1 over AN minus 1 over A. And now I can put it on a common denominator. So this is A minus AN divided by AN times A. So like that. Can write it like this. Right? Now already the denominator looks very promising because we know that this goes to 0. Right? And now, but now I need to bound this. So need to bound. Right? So need to bound. We need to bound. So we want to bound this here, right, by epsilon when little n is sufficiently large. The top, the denominator here looks great. The denominator, maybe we're a little bit worried about. But the thing is that, so we need to bound AN times A, this here, from below. Right, we want to bound it from below because then when you're looking at 1 over it, then that's an upper bound. Right? And really, because A here is just a fixed number that is not 0, then it's equivalent to proving. So this is equivalent to bound the norm of AN from below. Remember, we don't need to bound it from below for all AN, but we need to bound it from below for n sufficiently large. Right? And so now you make the trivial observation so that AN, you can write AN as AN minus A plus A. Right? And so therefore the norm of AN is bounded by the norm of AN minus A plus the norm of A. Sorry, this was not how I want to write it. I'm going to write it slightly differently. I'm going to write A. I'm going to do the symmetric thing, but I'm doing it, so I'm writing AN as A minus, so I'm writing A as A minus AN plus AN. Right. And then if I do that, then I can just take the absolute value of A is bounded by the absolute value of this difference plus the absolute value of AN. Right? And now I can move this here over on the other side. So this here implies that norm of A minus the norm of A minus AN is less or equal to this here, right? And now you see that this thing here is, so now we're going to use that this here was not equal to 0. So this here is bounded away from 0. And so now we can take, say, A here over 2. So we can use this here. We can use a norm of A over 2. This is a positive number because A was not 0. And we can use this in the definition of that AN. So use this. So use this in the definition of that AN converges to A. Right? So this means that if you are, this means that there exists a capital N, is called a capital N1. It's not the final N, that we want to use, but there exists a capital N1, so that if little n is bigger than this capital N1, then actually we have that A minus AN is less than this thing here, right? But now you see that this means that when you're looking at, when you go up here, and you're looking at, when you go up to that line before, so this is the line from before. Sorry, this here minus this here, this and this here. When you're looking at this line here, well, this thing here, this here is at most half of this. So this thing here is bigger than this thing here over 2, right? And so now you see that we have bounded these guys from below, right? And so now we go back up to, we're looking at C minus, we're looking at Cn minus 1 over A. This up here. I'm just transferring that equation down to this board here. So this here is A minus AN divided by, and I can just take the absolute value separately of the numerator and the denominator, AN times A. Okay, so now you see that this thing here, as long as, so when n here, little n, is bigger than n1, well then we have that this thing here is at the very least the absolute value of A over 2. So this means that this thing here we can now bound from above like this. This is as long as you have this inequality here. And this thing here, this is just a norm of A. This here gives another norm of A over 2. So the 2 jumps up. So it's like this thing here. Right? And now you see that this A is just like a constant, right? So this means that I may have to go even further out than N1, but if I go even further out, then I can make this thing here smaller than the given epsilon. Okay. Right, so this was like the outline, if you will, but that's not, at this point, there's not very much to fill in, right? Okay, so now I want to talk about subsequences. And then I want to prove a little theorem about subsequence. So so I have a sequence, and so I have a sequence. And then a subsequence. So I'll give you first some examples, and then I will explain, then I'll give you the proper definition of what a subsequence is. So I start with this sequence from before. So this was the sequence where A1 was -1, A2 was 1, A3 was -1. It was alternating between -1 and 1. And so in this case here, if you take the sequence, let's call it B. Let's use a different index. Let's call it BK. This is, right, so k here plays the same role as n before, but I want to use a different symbol to not somehow confuse with the n over here. So if I take, so I could take a sequence that was like 1 all the time, this here for all k. This here would be a subsequence. This would correspond to that you took all the even ones, right? That you just pick all the even ones, right? So this is like a subsequence. You could also have another example. So this is example 1, say. Another example is where you took all the odd ones. So this here is also a subsequence. And you could do something more elaborate where you take, say first, you take the first 2 odd, and then you take the next 2 even. So you could have a sequence that was like B1 is equal to -1, B2 is equal to -1, B3. Now it becomes the next 2 even ones. And then you go back to the next 2 odd ones, etc. Okay, that would be another subsequence. Let me look at a few more examples. So, for instance, if your sequence, your original sequence, so here's another example. If your original sequence was just that an was equal to n, right? Then you could take a sequence, so then the sequence where you just take the odd numbers. This here is a subsequence. And likewise, if you take all just the even numbers, this is also a sequence, a subsequence. Okay. But if you look at, say, something like this, where you're taking, so if you define a sequence where it was 1, 1, 1, 1, 2, even like this. This here is not a subsequence. This is not a subsequence. Because what you have done here is that you have taken the same number several times, and it doesn't appear several times. The value doesn't appear several times in the original one. So that's not allowed. It's also not allowed to do something like this. This here is also not a subsequence. Another thing that's not a subsequence, when you take things out of order. So if this here was the original sequence, if you're now looking at a sequence that was 3, 2, and then 4, 5, this here is, etc. This here is not a subsequence either, because things are taken out of order. Okay. So now, what is the formal definition of a subsequence? So here's a formal definition. So you have a sequence an, a subsequence of an is where you have a map G from n into n. This is an increasing map. This is strictly increasing. And then if you're thinking about this thing here, right, you think about this as a function f, then you now could think about the composition of these two functions. So this thing here, and maybe I would use a different notation like this, a different index like this. This thing here, bk, this here is a subsequence, right? So you see that this here, right, when you pick, if you have a sequence like this, you know, the first one could be anything in the original one. But once you have fixed the first one, you can't look back, or you can't go to this. You have to, the next element have to be somewhat further out in the sequence, okay? And that sort of continue, right? And this here is often just to indicate that it's a subsequence of this sequence. Then the standard notation is an and then another subscript. Okay, so anyway, so of course, hopefully there's not too many subsequences of sequences because each time it's supposed to be another subscript. Okay, now there's a little theorem that we can just prove here at the end. And that is that if you, and it's, yeah, it's sometimes, it's a very simple fact, but it is sometimes a useful fact. And that is that if you take a sequence, so a sequence, it's a theorem, that's a sequence an is convergent to A if and only if all subsequences of an converge to A. Okay, now to prove this, there's two things we need to prove, right? Because it's a if and only if statement. So we need to prove that if it is convergent, then all subsequences are also convergent. And then we need to prove that if all subsequences are convergent, then the original sequence is convergent. But one of the two implications is trivial. So one of the two implications is trivial. And that is that, namely, since, right, so the map, remember that the map to define a subsequence has to be strictly increasing, right? So remember that a sequence was a function like this. That was a sequence, right? And a subsequence, there you have another map that is strictly increasing. And then you're looking at the composition. But if you take this other map to be the identity, right, that the other map is like g of k is equal to k. Of course, this is strictly increasing, right? And if this here map was the identity, then the subsequence would just be the original sequence, right? So one of the two implications here is trivial, since an itself is admittedly trivial, but it is a subsequence. So if all subsequences converge to A, well then the original sequence, since it is a subsequence, suddenly will converge, right? So that was trivial. Okay, so we just need to prove that if an converges to A, then any subsequence. But this is not much more difficult because you see, if you, so given an epsilon, so now given epsilon, given, so now we have, so we now have that an converts to a. And we're looking at a subsequence a and k, and we want to show that a and k also converts to a. Right? So given epsilon greater than 0, there exists capital N. So that if little n is bigger than capital N, then an minus a is less than epsilon. But now you see that if k is bigger than capital N, then what corresponds to this here is the, right, this here, how to think about it, this here nk, you should really think about that this thing here is the value of this strictly increasing function, right? But this thing here is, because it's strictly increasing, is bigger than k, right? So you see that if this thing here is bigger than this, then means that this index here is further out than, in particular, the capital N. And so this means that if you have this here, then ANK, this is some element like this, but it's further out than capital N. So this thing here surely will also be less than epsilon because it's fall in under here. Okay, so that implication wasn't too much harder, and that's sometimes useful. That so like if it's sometimes useful that you're looking at a sequence and you see that if it is convergent, that you're looking at a sequence and you see that there's a subsequence that is not convergent, or you have that there's two different subsequences of a given sequence that converge to different limits than the original sequence wasn't convergent either. Yeah.
Can you not have like a finite subsequence of a convergent subsequence that like doesn't get to n, so it hasn't arrived at the point of convergence?
I mean, so convergence is always something about the tail, about the end, right? It never care about what happened in the beginning, right? So there might be finitely many ends initially where, you know, things are crazy, but then from there on out.
Okay, so the subsequences that we care about in this case are those subsequences that also exist.
Yeah, so all sequences, including subsequences, are infinite things, right? Yeah. So like, that's right. So because the thing is that you had to have this map, maybe I erased it, but G here have to be a map from all the natural numbers into N. So it means that for each element here, you get something, right? So there's really infinitely many of them.